This is section 3.1, part B, exponential functions. Your I can statement for this half of the section: I can solve problems involving exponential growth and decay. An common application of exponential growth is compound interest. The formula for compound interest is A is equal to P times 1 plus R over N raised to the N times T power, where P is the principal amount of money that you start with, R is the annual interest rate, we need to make sure that's written as a decimal, N is the number of times per year that it is compounded, A is the total account balance, and T is the number of years the money is in the account. Krysti invests $300 in an account with a 6% interest rate, making no other deposits or withdrawals. What will Krysti's account balance be after 20 years if the interest is compounded semi-annually, and then if it's compounded monthly? So our formula is A is equal to P times 1 plus R over N raised to the N times T power. Now P is your initial amount of principal, so that's the $300 that she puts into the account. R is your interest rate. It tells you the interest rate is 6%, but 6% written as a decimal, you take the decimal place, move it 2 places to the left, so this will be 0.06 for our interest rate. For part A, it says we are compounding this semi-annually, so that means twice a year. My N value on top is still 2, but the number of years is 20 years. So if you plug all that into your calculator, you're going to find that in her account after 20 years, she will have $978.61. Now we're going to do the same thing again, but this time it says we're doing monthly. So that means it's done 12 times per year. That's the only thing that's going to change. So instead of a 2, we are going to have a 12. And if we put that into our calculator, we're going to get $993.06. So if you are offered 2 different accounts, one is interest compounded semi-annually, one is interest is compounded monthly, monthly is going to make you more, not a whole lot more, but it will be more money because they are compounding it more frequently. So that means they're generating how much interest it earns in a more frequent pattern. Now, if they do continuous compound interest, so that means it is always earning interest, not just semi-annually or monthly or anything like that, or even yearly. This means it's doing it continuously. Our formula is A is equal to P times E raised to the RT power. E is your irrational number that we discussed earlier in section 3.1 part A. R is your annual interest rate. Again, make sure you write that as a decimal. P is still our principal, and T is the number of years. Suppose Krysti finds an account that will allow her to invest $300 at 6% interest, and it is compounded continuously. If there are no other deposits or withdrawals, how much money will she have in 20 years? So the exact same information, but this account is continuous instead of semi-annually or monthly. So our initial principal is still $300. Our interest rate is still 6%. And we still have 20 years. And if you put all of that in your calculator, you're going to get $996.04. So again, a little bit better than what we had on semi-annually and just a tiny bit better than what we had on monthly. But if you do compound continuously, it will have a higher value. Now, we don't just have to use growth and decay problems with interest and money. You can also use them in other areas. Exponential growth or decay, if it is an exponential rate that is not continuous, we're going to use n is equal to n sub 0, which is your initial quantity, times 1 plus r raised to the t power. If it is continuous, we're going to do n equals n sub 0 times e raised to the k t power, where k in this one is still your exponential rate. Make sure you're still writing that as a decimal. Now we're going to know the difference between growth and decay. If on just the exponential growth and decay, if the r value is greater than 0, it's going to be growth. If it's less than 0, it's going to be decay. And the same with our k value for the continuous function. If k is greater than 0, it's growth. And if k is less than 0, it will be a decay problem. Mexico has a population of approximately 110 million people. If Mexico's population continues to grow at the described rate, predict the population in Mexico in 10 years and in 20 years. So the first one says they're going to increase at 1.42% annually. That's our R value, but remember we're going to write this as a decimal. We move it 2 places to the left. So it's going to be 0.0142. And we're going to do this twice. The first time at 10 years, the second time at 20 years. Now this is not continuously, it does say annually. So our formula for this one so our n sub 0 is your initial amount. That's our 110 million. Our rate is 0.0142. And the amount of time, first we're going to do it 10 years, and then we're going to do it 20 years. And we call that n sub 10, so we know this is the 10th year. And after 10 years, we're going to have 126 million. 656,869 people. Now let's do the same thing again and see what would happen in 20 years. The only thing that changes in this case is our t value, and we plug this in. In 20 years, the Mexican population can be predicted to be 145,836,022 people. So this is if it's not continuous. This is only done annually. That's why we don't have to know how many times per year. This is just done annually, so we just need t, the number of years this is happening. We do not have an n value. Now we're going to do the same thing, but this time it wants continuously. If it's continuously, our formula is n equals n sub 0 times e to the kt power, where k is just your rate again, which would be 0.0142. Again, we're going to do this at 10 years and at 20 years. Our k value, we said, is 0.0142. And we're going to do this at 10 years and then again at 20 years. At 10 years, we're going to have 126 million. 783,431 people. Now, if you still have written down the previous one, if this was done annually, it was 126,656,869 people. So it is about 100,000 less people if it's done annually instead of continuously. Again, we can do the same thing with 20 years. We have 146,127,622 people. The table shows the number of reported cases of chickenpox in the United States in 1980 and in 2005. If the number of reported cases of chickenpox is decreasing at an exponential rate, identify the rate of decline and write an exponential equation. So first, let's identify the information we have. Let's call 1980 year 0. So then 2005 is 25 years later, so we're going to call that year 25. So we know our n sub 0 is equal to 190.9 thousand cases, and our n sub 25 is 32.2 thousand cases. Now, this doesn't tell us it's compounded continuously, so we're just going to use non-continuous. So we have n sub t is equal to n sub 0 times 1 plus r to the t power. Now we know our n sub t in this case is going to be 32.2. Our n sub 0 is 190.9. And we know that it's 25 years later. So the first thing we want to do is try to get that r value by itself. Right now we have 190.9 times that quantity. So to do the opposite of that, we are going to divide. On the right side, those 190.9s are going to cancel. On the left side, let's just go ahead and leave that as a fraction for now. The next thing we need to do is get rid of that 25th power. So that means we need to take the 25th root of both sides. Because it is an odd number, we do not have to do plus or minus. Now, if we take the 25th root of that value, we are going to get 0.93, and there's some more decimal places after that. We need to get the r value by itself, so we are going to subtract the 1 from both sides. So we will get an r value of negative 0.07. So this tells us it is decreasing, which we expected. So if we go back and write our equation to figure out how many cases of chickenpox there will be per year will be n is equal to 190.9 times 1 plus a negative 0.07 raised to the t power. Now remember, this is our cases in thousands. So whatever value you get, if we got 50, that would be 50,000. So remember, since we didn't change those to thousands, you do need to make sure that happens in your answer. Now we're going to use the model to predict the number of cases will drop below 20,000. So to do this, we are going to graph your original function that we just wrote the equation for, and you're going to look for a y value that is less than 20,000, which, since these are written as decimals, this means we're looking for a y value that is less than 20. And if you graph it, it's going to be approximately at year 32 that this will be below 20. Remember, year 1 was 1980. So year 0 was 1980. So 32 years later would be in 2012. So we will predict the number of cases of chickenpox will drop below 20,000 in the year 2012.